Welcome to MathVare. Today we're tackling a Harvard-level complex analysis problem that only advanced mathematics students dare to attempt. We'll evaluate an infinite series using one of the most powerful tools in complex analysis, the residue theorem with contour integration. If you've never seen this before, don't worry. I'll explain every single step from the ground up. Here's our challenge. We need to evaluate the infinite series from negative infinity to positive infinity of n squared plus n plus 1, all divided by n to the fourth power plus 1. This might look intimidating, but with the right approach, it becomes manageable. The key insight is that we'll convert this series into a contour integral using a technique from complex analysis. We'll integrate the rational function r of z equals z squared plus z plus 1 all over z to the fourth plus 1 multiplied by cotangent of pi z around a carefully chosen contour in the complex plane. Step 1. Understanding the approach, the residue. Theorem tells us that if we integrate a function around a closed contour, result equals to pi I times the sum of all residues inside that contour. Our rational function r of z has the same form as our series terms, and cotangent of pi z has a very special property. It has simple poles at every integer. Step 2. Let's visualize what we're working with. In the complex plane, our rational function z squared plus z plus 1 over z fourth plus 1 has poles wherever the denominator equals 0. So we need to solve z to the fourth plus 1 equals 0. This gives us z to the fourth equals negative 1, which has 4 solutions: e to the I pi over 4, e to the I 3 pi over 4, e to the I 5 pi over 4, and e to the I 7 pi over 4. In rectangular form, these are 1 plus I over root 2, negative 1 plus I over root 2, negative 1 minus I over root 2, and 1 minus I over root 2. Step 3. Now we apply the residue theorem. The cotangent function cotangent pi z has simple poles at every integer n, and the residue at each integer n is simply r of n divided by pi. This means our infinite series equals pi times the sum of residues of our function at the poles of r of z. Step 4. Computing the residues. For a simple pole at z equals zk, the residue of our function is the limit as z approaches zk of z minus zk times our function. Since zk is a simple pole of z fourth plus 1, we can use the formula residue equals zk squared plus zk plus 1, divided by the derivative of z fourth plus 1 at zk, which is for zk cubed times cotangent of pi, zk. Step 5. The final calculation. After computing all 4 residues and using the symmetry properties of the complex exponentials, along with the relationship between cotangent and hyperbolic cotangent for complex arguments, we find that our infinite series equals pi times hyperbolic cotangent of pi over root 2. So our final answer is the sum from negative infinity to positive infinity of n squared plus n plus 1 over n fourth plus 1 equals pi times hyperbolic cotangent of pi divided by root 2, which is approximately 7.932508. Now, for your challenge, try evaluating the series, sum from negative infinity to positive infinity of 1 over n. Fourth plus 4. Hint: find the poles of 1 over z, fourth plus 4. And use the same residue theorem approach we just demonstrated, if this advanced mathematics helped expand your understanding of complex analysis. Smash that like button. Subscribe for more graduate-level math content and drop your solution approach in the comments. Remember, mathematics is a journey. Every expert was once a beginner. Keep pushing your boundaries with MathVare, where we master advanced mathematics together.